In this video, we'll go over a brief introduction of the binomial series. Now first, let's talk about the non-negative integer example. So let's first consider the case where we have the binomial functions of the form f of x equals to the quantity 1 plus x raised to the r. And we first look at the case where r is a non-negative integer. So like going through the cases, okay, what if r is 0, 1, 2, 3, 4, 5? So f of x for the first one would be 1 plus x that raised to the 0, which is equal to 1. Then it would be f of x equals to the quantity 1 plus x raised to the first, which would just be 1 plus x. The next one would be f of x equals to 1 plus x, that quantity squared, which is 1 plus 2x plus x squared. Then the f of x is equal to the quantity 1 plus x raised to the third, which is 1 plus 3x squared plus x cubed. Then f of x equals to 1 plus x, that quantity raised to the fourth, which is 1 plus 4x plus 6x squared plus 4x cubed plus x to the fourth. And then for the last one we're doing, let's say if we had f of x equals to the quantity 1 plus x raised to the fifth, that's 1 plus 5x plus 10x squared plus 10x cubed plus 5x to the fourth plus x to the fifth. Now one thing, looking at this pattern first, if you've seen Pascal's triangle, then you'll recognize the coefficients of these polynomials functions. Now in general, if you have f of x equals to the quantity 1 plus x raised to the r, then that's equal to the sum as n goes from 0 to r of r choose n over x to the n, where that r choose n notation is equal to r factorial over n factorial times r minus n factorial. Now if you taken probability or statistics course, you will have seen this binomial coefficient. Now what it turns out in general is that by using Maclaurin series, that it's not just for the case when r is a non-negative integer, it's actually for the case if r is any real number and the absolute value of x is less than 1, then that quantity 1 plus x raised to the r is equal to the sum from 0 to infinity of r choose n times x to the n. Which, if you look at some of the first two terms, that would be 1 plus rx plus r times r minus 1 over 2 factorial x squared plus ... Then the n plus 1 term would be r times r minus 1 times ... times r minus n plus 1 all over n factorial times x to the n plus ... and it goes on forever. So like I said, this is no longer the case we're just talking about non-negative integers, but we could have, okay, what if r is 1/2, or what if it's negative 2/3, and so on. So that's a very useful thing to have, because we'll be able to build up many other series using this form. So let's look at an example. For this one, you're to find the Taylor series of f of x equals to 1 plus x squared raised to the 1/3 about a equal to 0, and write out the first 4 terms of the series. Now first, the Taylor series is given by the sum from n equal to 0 to infinity of 1/3 choose n over, times x squared that raised to the n, which would be the same thing as the sum from n equal to 0 to infinity of the 1/3 choose n times x to the 2n. So the first 4 terms of the sequence would be 1 plus 1/3 x squared plus 1/3 times 1/3 minus 1 over 2 factorial times x to the fourth. Because remember, it's x squared to the first, and the next term would be x squared to the second, then x squared to the third. That's how we're getting the powers of x's. So the last of the 4 terms would be 1/3 times 1/3 minus 1 times 1/3 minus 2 all over 3 factorial times x squared. So simplifying that, that would give you 1 plus 1/3 x squared minus 1/9 x to the fourth plus 5 over 81 x to the sixth. Now, just how good of an approximation is this using these first four terms? Well, let's look at it two ways. First, let's actually look to the graph on the right, where the graph on the red is the graph of the function, the 1 plus x squared, that quantity raised to the 1/3. So it's like a kind of a curve that goes downward and then goes back up at x equals to 0. And then if we were to graph the function of those first four terms, that would be the one in blue, which almost looks like a parabola. But if you notice that around 0, that those two graphs are very close to each other. Now, another way we could look at how close are they, and this should have been not the square root of 1.25, that should have been the cube root of 1.25. So if you had the cube root of 1.25, which is 1 plus 0.5 squared to the 1/3, so we're plugging in 0.5 in for our x into that function, that's equal to 1.0772.173 ... goes on forever. And then if we were to plug that 0.5 in for x into that approximation of using those first four terms, that what we would get is, well, it'd be that 1 plus 1/3 times 0.5 squared minus 1/9 times 0.5 to the 4th plus 5/81 times 0.5 to the 6th, which would be about 1.077353339 ... and also goes on forever. But if you notice, those are very close. That is a very good approximation. And if we had gone even further to find, let's say, maybe the first 10 terms of the Taylor series, then we would have gotten an even closer approximation to that value.